Hi learners, welcome back. This is the last part of Capillary Electrophoresis, part 4 of this advanced analytical technique. Here we're talking about buffers and columns for CE. So we start with first about electrolytes that contains your buffers to answer some questions. How to choose suitable buffers? What are the differences between the micelles and microemulsions for electrokinetic chromatography? What are the oil in water and water in oil microemulsions? What are pseudo-stationary ion exchange phases for CE? What are CE selects and non-selects used for? And these labels are very easily found on some of the parts of CE instruments. First, how do we select buffers and columns for CE? Why are they used for? Because the buffers are inside here to run your capillary electrophoresis, they should be optimized to enhance selectivity of your analyte. Now, there are many buffer additives used to improve separation because you do not want your peaks to merge together. You want them to be fully resolved. Now, normally, uncoated capillaries, these few silica SiO capillaries, can be used for separation based on charge to size ratio, but sometimes we need to do some internal coating like we have discussed in class, so that it's necessary to prevent adsorption of the surface. There are also packed columns used for CEC, and gels are also used for size sealing. Electrolyte system for CE. There's a few parts here. One is the buffer, one is the micellar media, inclusion additives, complexing additives, and other types of media, and how it will affect the electrophoregram at the end. So first, buffers aren't something new to us. Buffers are chemicals that can allow the system to prevent a drastic change in pH because they themselves have the base and conjugate acid, or the acid and conjugate base here, to absorb the addition of a small amount of acid or bases to it. Some of the buffers commonly used in CE are your phosphate 1. This is under the acidic range 1.1 to 3.1, acetate, phosphate 2, borate, right? And why are there even two kinds of phosphate? Because phosphate comes from phosphoric acid, that's a tribasic acid, so there are 3 dissociation points. Now, when there are 3 dissociation points, the pH range is different. So here we're talking about the most acidic side of the phosphate group. We also have the Zwitter ionic buffer kind, the MES, which is the 2N-morpholino ethane sulfonic acid, and the tris. Tris is a very commonly used buffer in CE, your tris hydroxymethylamino-methane, tend towards on the alkaline side. For CEMS, we try to use volatile buffer because in the end, for the MS part, we need to vaporize it. So what are some of these good volatile buffer additives? Include your ammonium acetate, ammonium formate, acetic acid, trifluoroacetic acid, and ammonium hydroxide. This is just your ammonia, right? Aqueous ammonia. So this TFA, and to choose them, you look at the pH range you want your system to be in. As you can see here, for these two, they are pretty close, 5 to 6, 6 to 7 here, and it's all because of the conjugate base of the acid group here, whether you have a formate or you have acetate. So the choice of buffer really depends on a few factors, not just we like the name or what, but solubility and stability of analyte in electrolyte. Suppose your analyte, right, cannot dissolve in buffer, it forms a precipitate, you cannot choose the buffer. And to do that, you need to do some trial and error. So the first thing, most important thing is, it must be soluble, at least visible to the eye. There are no precipitate. How do we check the stability? Once you add it into the buffer, if you see a color change, which means that there might be some dissociation, chemical reactions that's not stable. Next is, how much can your analyte ionize? Because after all, your analyte must be ionized, must be charged in order for it to move, right, from the inlet to the outlet by the action of the coulombic charges. If it doesn't ionize, it's just a bulk molecule that's unaffected by the current, then how do you separate? We also like to investigate the influence of anions and cations present in the electromigration of solutes, pH, effect on organic modifiers, and other additives, and of course, dissipation of heat. So let's recap a bit. This is under more general chemistry under acid-base equilibria. So for ionization of analyte, right, for weak acid, we define as your HA, and in the presence of water, it will dissociate partially because it's weak to form an H3O plus and A minus, that's the conjugate base of HA. So the higher the dissociation, the equilibrium position lies on the right hand side more. You have a higher concentration of a H plus ion and your A minus. So at equilibrium, the concentration of HA is equals to the concentration of is A minus Ka prime minus H plus. So K, this is the dissociation constant for weak acid, right? Is the sum of these two concentrations over the initial amount here, because it's what you have at the end. Alpha is your degree of dissociation, how much of it has dissociated. So it's C concentration of this A minus over the concentration of A prime, okay, at equilibrium. Mu A prime is the observed mobility of A, right, and mu A is your intrinsic mobility of A. Okay, so here's the formula for you to do some calculations there. Next part, similarly for your weak base, we denote as B. B gains H plus because it's base. Here we're talking about the Bronsted Lowry, gains H plus and forms hydroxide. So equilibrium, the concentration of this base is equals to this amount, and here we have the base dissociation constant. So again, it's the converse of the previous slide for the acid. So the concentration distribution, the peak shape, can be related to relative mobility, okay, which is the ratio of mobility of solute relative to that of the buffer. So here in this graph here, you see the dependence of the relative effective mobility and the degree of dissociation alpha on the pH of a weak monovalent acid. This is the equation for the capacity factor. Under most conditions, the capacity factors must be adjusted to between 0.5 and 10. A large capacity factor means that the major fraction of the analyte is incorporated into the micelle, and it is necessary for the analyte to be distributed evenly between the micellar and the aqueous phase. In other words, the analyte must not spend most of its time in one phase. Here, this is the equation for the resolution, equation for the MEKC, where N is your theoretical plate number. This S stands for the separation factor. So this equation predicts the effect of the N number of plates, your S, your K prime, and your T0 over T MC. MC stands for micelle, okay, on the resolution. And the effect we can discuss later. So you see here, we put the label in blue because these are the K prime and R for HPLC, not in this module but previously. The red are the additional term for MEKC, because now we have this micellar electrokinetic system. Now in MEEKC, unique, right? These are typically achieved using the microemulsion composed of this nanometer-sized droplet, oil suspended in the aqueous phase. It is suspended because, right, it's a hydrophobic oil in a aqueous buffer that's very charged, so it forms a little sphere to minimize your surface tension. So these oil droplets are coated with the surfactant molecules, and the system is stabilized by the addition of this short chain alcohol surfactant here. The short chain, right? So the exterior now is a bit more polar. They can interact with, your water aqueous phase. If not, it's just very unstable, just repel. So here you can see it's a schematic diagram of an oil in water in a microemulsion droplet. Okay, these are the charged particles that get attracted. Okay. Now the difference in a water in oil microemulsion is that, right, so now the tail face outwards here. So instead, the sphere, right, because the bulk phase is oily, is hydrophobic, so the tail will interact better outwards, but then the hydrophilic head will face inwards here. So what you see is still a droplet, but it depends on the environment. It will just change as an adapt. So on the right hand side, this is called more the reverse microemulsion. The left is the normal microemulsion. How does it work with the CE here? So it applies the same principle within the capillary. We know that, right, since all of them are negatively charged, right, they will tend to be attracted to the anode. Right? But the thing is, when it's smaller, when the size is smaller, it gets carried, right, to the anode a bit more as it follows the EOF. So for hydrophilic analyte, it will stay in the aqueous phase, right, and follow the EOF and become have a faster migration. For the hydrophobic analyte, because it entered the microemulsion droplets in this manner, right, it's big. Now it has also more charge. It gets attracted by the cathode here, and that's why it's slower, because it gets pulled back. So a comparison between the MEKC and MEEKC, this E, okay, one single difference, right, is that in MEKC, separation of neutral solute is due to interaction of dissolved molecules with hydrophobic core of ionic micelle. Solute penetrates the surface of MEKC microemulsion droplets more easily than that of the MEKC micelle. So MEEKC has a wider function. With extra E, MEEKC MEEK, it has a more superior separation efficiency, and most likely due to improved mass transfer between the microemulsion droplets, because now we have a co-surfactant mediation. And the MEEK also offers a larger separation window, and the size of this window can be controlled. Therefore, potentially, we have better separation peaks compared to MEKC. But the thing is, the phase equilibrium, because now we have dissociations, is a bit more complicated. So, and we talk about next how the different kinds of potential reaction dissociation will cause complication. Okay. So here is a diagram in MEEK, right? Now on the scale at the bottom, this is the hydrophile lipophile balance here. So on the left here, this is more the space is more aqueous and polar. On the right side, the space is very non-polar here. So the bulk phase is lipophile. Here the bulk phase is hydrophile. So you see, as we talked about just now here, right, your surfactant, how does it form your droplet here, right? If the exterior bulk phase is hydrophilic, the head has a hydrophilic phase outwards here, but on the other side, the tail phase outwards. So here in the middle, you have the hydrophile equals to lipophile, which is in a way the half-half. So in the middle, you see a phase that's in between both. And if you can recall, it's something like a separation funnel in a synthesis, right? Where sometimes when you shake it between the aqueous and organic layer, in the middle, there's a bit of a cloudiness. That's something it's still trying to resolve here. But if the polarity between the two phases, the aqueous and the organic phase, then it becomes more distinct in this manner here. Hope you're trying to relate to what you have seen in the lab before. Just a bit of name. Windsor 1 is this type, Windsor 2 is that type. Some concrete example of an electrophoregram. Okay, look at the structure of this molecule and try to analyze the difference. For instance, here you see a SIM group, primary amine, secondary amine, let's say a tertiary amine. Right? How does it affect the migration time? Right? Here we have some surfactant to disperse the molecule. Right? Notice the font typeface in a blue color. Okay, about the additive there. Another example, which is the use of SDS and then other additive. So we have got your SDOSS, sodium dioctyl-sulfosuccinate, MAPS, and twin 21 is a trademark chemical. So with more co-surfactant, what happens is the order of the migration of this analyte also different. Maybe FA is the same for the front part, formic acid, but towards the end you see 9, 10, 12, 13, here is 10, 9, 13, 12, and these are somehow rearranged, right? So why does it matter? What if we are trying to isolate certain particle that's of higher percentage here, right? We want to save time. We don't have to stop at all the way until every single parts of the mixture has been eluted. Next, comparing the pH, right? An extreme pH and the low pH, again you see a difference in the order of migration of your analyte there. Okay, so at the low pH, your BB comes out first, and the high pH, this is not very extreme in your meat, the BB comes second last. So besides that, you see that right in the first peak, right here, there's a faster separation at the high pH, right? You finish all your elution at about under 7 minutes, but here is more than 7 minutes. Okay. Also, the other thing you should maybe notice is the peaks here are much more sharper. Right here you see a bit more width in the peaks. Okay, this is not so pretty here. Here you see the reverse microemulsion, water in oil, so which is your reverse microemulsion. And what you see is that inside here there's a neutral molecule, and the neutral molecule becomes solid. They don't migrate in order of hydrophobicity, because when there's no charge they just go with the EOF, which means this is offering some form of selectivity, where your molecule has a highly hydrophobic neutral compound, because you don't want them to influence your migration. So again, pay attention to the electrolyte additive here. Next part, talk more about ion exchange, ion pairing. So these are just equations where you would like to understand the ions that are free or ions that are paired. Why would ions be paired? If you have cation and there's presence of anion, which is very common for buffer, normally it goes in tandem because of the Coulombic attraction. Okay, so in this case, right, this capital F here stands for the fraction of the another ion that's free from a polymer that's in a way isolated. As usual, your capital K here is your kind of equilibrium constant. So IP stands for ion pair, right? So you see this KIP, okay, KIP is about how the equilibrium of how easily does it form an ion pair, compared to on the left hand side of the equilibrium where it's free. When it's single, just S minus and P plus. But on the right hand side, when it's combined, it's S minus P plus together.